In this video, we're going to examine the conformations of cycloalkanes up to cyclohexane, the six-membered cyclic alkane. And with the cycloalkanes, essentially what we do, one way to think about it is we take a linear alkane and we tie the ends together, creating a carbon-carbon bond and losing two hydrogens. The good news with this in terms of conformation is it restricts the motions available to the carbon chain, right? No longer can we really freely rotate all the way around bonds because the carbon-carbon bonds are constrained to be tied together. And so there's not entirely free rotation around single bonds in most cycloalkanes. And the smallest cycloalkane, cyclopropane, as we'll see, is severely locked. So we don't have to worry so much about staggered and eclipsed conformations interconverting with the cycloalkanes. What we'll find is that they tend to be locked into staggered or eclipsed arrangements, as the case may be, and these strains actually are a source of instability for the cycloalkanes. So for example, cyclopropane, as we'll see, has very severe eclipsing strain because its CH bonds are necessarily eclipsed. Now that would be the case for all four of the cycloalkanes that you see on this slide were they planar. But with the exception of cyclopropane, which is necessarily planar, right? 3 carbons and 3 points define a plane. Cycloalkanes are not planar. The rings bend and sort of kink themselves to alleviate strains, alleviate eclipsing strain, for example, and alleviate angle strain that would be associated, for instance, with trying to achieve a 90-degree bond angle in cyclobutane, which is very far from the tetrahedral 109.5-degree bond angle that those carbons want to have. So, and you can see in the three-dimensional images on these slides that the conformations of cycloalkanes are not planar, they're bent. The good news is it's a smaller number of conformations to deal with in each structure than, for example, we saw with butane, with linear acyclic butane. So, for example, cyclopentane has basically one important conformation. It's known as the envelope, and it's the conformation that minimizes the energy under the constraint that the carbons, the 5 carbons, are linked together in a cyclic array. So, for the rest of this video, we're going to go through the remaining cycloalkanes and look at their most stable conformations and the sources of strain within each. We're also going to talk about the stabilities of the alkanes on a per methylene basis, basically taking off the table the fact that we're adding CH and CC bonds as we add a carbon. If we look at the per CH2 stability of the cycloalkanes, we'll notice an interesting trend and an interesting dip at cyclohexane, which is a very, very special cycloalkane and one that we're going to spend a lot of time exploring toward the end of this unit. What we can do with the cycloalkanes is look at their heats of combustion to get a sense of stability. We noted previously that the less exothermic the heat of combustion, the more stable the compound is, particularly when we're looking at isomers, which have the same numbers of carbons and hydrogens. We can do an analysis like this of the cycloalkanes, but look at the enthalpy of combustion per CH2 group in the cycloalkane. This eliminates, again, issues with we're making more CO2 and H2O as we add a CH2 group to the compounds. And if we do this and plot the heat of combustion per CH2 group as a function of the ring size on the x-axis, we see something very interesting. The small rings have relatively high heats of combustion per CH2 group, indicating quite a bit of instability. The higher this bar, the less stable the compound, right? Since we're talking about a less stable starting point giving rise to a more exothermic heat of combustion. So cyclopropane is at the top of the heap, the least stable cycloalkane. But as we get to 5 and 6, we get to much, much more stable rings, with the 6-membered ring being particularly remarkably stable. So these medium ring sizes, 5, 6, 7, and 8, are generally the most stable and most common as a result of their stability ring sizes that we find in organic compounds. Beyond 8, we get to the so-called large ring sizes, and these are a little bit less stable than the 5 to 8, the medium rings, but not that much, right? We're not back to the case of cyclopropane or cyclobutane at all. These large rings have a lot more conformational flexibility, and as such, they tend to not have as many strains as the small, more constrained rings. But by and large, beyond this chapter, we'll live in this medium ring territory with 5 and 6 membered rings, extremely common in organic compounds. And in the small rings, it's sources of strain due to their constrained, sort of locked structures, locked cyclic structures, that give rise to this instability. When we talk about strains in cycloalkanes, there are three categories of strain that are important to consider, and these differ in the type of motion that would alleviate the strain, is one way you can think about this. Torsional strain, we've already seen. We can theoretically alleviate torsional strain via rotation about a bond. Another term for this essentially is eclipsing interactions. So for example, in the structure of cyclopropane, which is necessarily planar, we've got two pretty bad HH eclipsing interactions in this compound, and that's a source of torsional strain. Now, in the cycloalkanes, angle strain can also be a problem, particularly for the small rings. Angle strain can be adjusted by adjusting a bond angle, theoretically again, but with the cycloalkanes, sometimes that kind of angle adjustment is not possible. So angle strain is associated with non-ideal, you can think about it like non-Vesper theory bond angles. So again, cyclopropane, if we look at this planar structure, it looks like the bonds have a 60-degree angle between them. That is way, way far from the 109.5-degree bond angle we would expect for tetrahedral carbon. And that is a source of instability, and we call that angle strain. Steric strain refers to the repulsion that electron clouds experience when they come close to one another in space. And one place we'll see steric strain is in groups attached to cyclohexanes that are relatively close in space. These groups are closer in space than they may appear in the drawing, and if the substituents are large, even something like CH3, we can get some steric repulsion between these groups, which is a source of destabilization, and we call that steric strain. Any sort of steric repulsion between groups that we can't alleviate via rotation about one single bond or a bond angle adjustment. We lump it all into steric strain. Now we're going to survey the conformations of cyclopropane, cyclobutane, and cyclopentane, and touch on cyclohexane briefly, which is going to get its whole own video because it is very special, being the strain-free cycloalkane. But let's start with the smallest cycloalkane, cyclopropane, C3H6. Necessarily planar, and so it's severely affected by angle and torsional strain, and it's quite rigid. Now, we mentioned that it looks like the bond angle in cyclopropane has to be 60 degrees, equilateral triangle, right? But in fact, the carbon-carbon bonds are actually a little bit bent in cyclopropane, and this alleviates some angle strain. So the angle between the hybrid orbitals forming the bonds is not actually 60 degrees. It's somewhat larger than 60 degrees, but it's still pretty bad, right? We're talking maybe 80, 90 degrees, which is still quite far off from 109.5. So there's still severe angle strain in cyclopropane. We'll also notice, particularly if we look at a Newman projection, look down one of the CC bonds in cyclopropane, that its CH bonds are severely eclipsing. They're necessarily eclipsed because the molecule has to be planar. And so we get interactions like this, CH-CH eclipsing interactions. We've got two of those that we can see in this Newman projection, and actually quite a few more. And so if we look at the energetic situation back here, we can see that relative to the strain-free cyclohexane, cyclopropane is about 40 kilojoules per mole higher in energy than cyclohexane. And that's all due to strain. And this is per CH2 group. Now, each CH2 group is associated with two hydrogen-hydrogen eclipsing interactions. For example, this CH2 right here has an eclipsing interaction here and an eclipsing interaction here. We previously noted that those are worth 4 kilojoules per mole each, right? So we could sort of decompose this 40 kilojoules of instability into the 8 kilojoules per mole due to the eclipsing interactions, and then the angle strain, which is basically responsible for the rest, a whopping 32 kilojoules per mole. So cyclopropanes are actually liable to open, particularly when you put substituents on adjacent carbons that sort of tug on the bonds and create polarization within the ring that allows the bond to break heterolytically. The situation in cyclobutane is actually not quite as bad as in cyclopropane. So the natural sort of bond angle in cyclobutane, if you think of it as a planar structure, is something like 90 degrees, severe angle strain. And again, if we think about the completely planar structure, just like in cyclopropane, this would imply severe eclipsing interactions between the CH bonds. They'd be sitting right on top of each other. This is the only way to achieve planarity. That eclipsing interaction is pretty bad energetically speaking. And so what the molecule does to lower its energy is actually pucker a little bit. We can see in the actual structure, in the true most stable conformation of cyclobutane, there's a bit of a puckering. This actually compresses the bond angle from 90 to 88 degrees, but it alleviates eclipsing interactions. It rotates, for example, these groups out of exact eclipsing alignment with the CH2 group in the back. So puckering is a stabilizing effect in cyclobutane, and you get this kind of butterfly-looking structure as the most stable conformation of cyclobutane. And the bond bending here is not as extreme as in cyclopropane, and the carbons are actually almost perfectly sp3 hybridized as a result of the bond bending, which is quite nice. So there is some angle strain here, but it's not as severe actually as it is in cyclopropane. With cyclopentane, we're getting closer to this strain-free ideal. And actually, if you do the math on the angles in a regular pentagon, the geometry, you'll realize that in an ideal pentagon, I believe the ideal angle is something like 109 degrees or 108 degrees. So we are very, very close to the ideal tetrahedral bond angle here. So that suggests there's very little angle strain in cyclopentane. But again, the problem with a perfectly flat cyclopentane ring is that the CH bonds would be eclipsing, and that eclipsing strain, that torsional strain really adds up when you're talking about 5 carbons, 10 CH bonds, right? All of which are eclipsing each other. To avoid those problems with eclipsing, the cyclopentane molecule actually folds a little bit. And it kind of folds up on one side to create what we call the envelope conformation. This is the most stable conformation of cyclopentane. And it's an envelope in the sense that 4 of the atoms are almost coplanar, kind of like the flat side of an envelope. And there's one carbon that sort of sticks up, like the flap of an envelope. So this picture is kind of meant to evoke this idea where this carbon is like the flap of the envelope, kind of folded up, and the remaining 4 carbons kind of form the bottom of the envelope, where you put the letter, so to speak. So cyclopentane, we have the envelope conformation, and this is still not quite strain-free. We've got some eclipsing interactions. For example, here we can see some pretty significant eclipsing interactions at the bottom, so to speak, of the envelope. So cyclopentane even still has some problems. Finally, when we get to 6 carbons, we reach the strain-free cyclohexane. Cyclohexane can adopt a strain-free conformation, and in our energy graph of the heat of combustion per CH2 group as a function of ring size, we see cyclohexane coming in at the energy minimum. This is the most stable cycloalkane. It's essentially strain-free, and Newman projections of cyclohexane can help us see why this is the case. If we look down, for example, one of these carbon-carbon bonds, this is the Newman projection we see. It looks like 2 Newman projections in one because we're actually looking down 2 bonds at once, this bond and this bond. So we see Newman projections of both of those bonds. And notice we've got a perfectly staggered arrangement of the CH bonds and the CC bonds here. And that perfectly staggered arrangement is why this is an energy minimum. There's absolutely no torsional strain in cyclohexane at all. It's also possible for the ring carbons to assume an ideal tetrahedral bond angle of basically 109.5 degrees, so there's no angle strain in cyclohexane either. This particular conformation that is free of angle strain and torsional strain is known as the chair. And this is a very important structure in organic chemistry. 6-membered rings, because they are strain-free, are ubiquitous. They show up all over the place, both in stable compounds and in transition states of reactions where there's a partial bond associated with maybe even a temporary 6-membered ring. So 6-membered rings are ubiquitous, and we're going to spend a lot of time in the remainder of this unit learning to draw chair structures and interpret chair structures properly. And so just to give you a sense of why this is called a chair, imagine a little person kind of laying across the chair like this with their legs down here and their arms up here. So this carbon looks like the head of the chair, and this carbon looks like the feet of the chair, so to speak. It's sort of like a chase lounge chair or like a chair you find at a pool or something like that. This is why it's called the chair structure. In the next video, we're going to examine the conformations of cyclohexane in more detail. The chair is the most stable conformation, but is not the only conformation of cyclohexane. And we'll also see that for any cyclohexane, there are actually two chair structures possible, which differ significantly for substituted cyclohexanes, in which we replace one or more of these hydrogens with some R group.